screen. I think we were in this slide in the last class, isn't it?
Yes.
Okay. So let's start the class. We have done all these things, and today we will start with this expected value. Okay. We'll start with this expected value of these family of random variables. All right. The thing is, when we're talking about the expected value,
Sir, your
yes.
volume is a bit low.
Can you listen to me?
Yes, sir, but the volume is very low.
But just now I have taken the class like this.
Yes, sir. Now it's
They
okay.
haven't complained.
Now it was okay.
Now it is okay.
Yes, sir.
Okay. The thing is, expected value. What is the expected value? What does it mean by expected value? Expected value of x is equal to xpx summation. Already in the last class, I told you in the expected value equation that the mean value can also be taken by using the expected value when we are having the random values with their probabilities. Okay, so this expected value is the xpx summation. That is the way we solve the expected value. And the thing is, we have 6 random variable families, and for all these families, we have their PMF. When we have their PMF, then from the PMF, we can easily find out the values with their corresponding PDF or PMF, isn't it? Or the probabilities. So for a Bernoulli random variable, look, they have already told you that the expected value equals to P. We need to prove it. We need to prove this one. How to prove it? What is the PMF of the Bernoulli random variable? It is definitely the PXAX will be equals to P for x equals to 1, then 1 minus P for x equal to 0, and then 0 otherwise. If you can remember. Can you remember that one?
Yes, sir.
All right. So the thing is, the PMF is something. Anyway, don't talk. Don't talk.
Sir, please mute everyone.
Carrying stuff করতে হবে না? All right, the thing is, so we have to write again. This is the problem. So let's write it again. The px was something like p for x equals to 1, 1 minus p for x equal to 0, and then 0 otherwise. That is the PMF for the Bernoulli random variable. Can you understand? This is the Bernoulli random variable PMF. Now we know to find out the expected value, what we need is to take xpx summation, isn't it? Now what is the value of x? Look at that value of 1 when the probability is p. So 1 into p plus when value is equal to 0, then the probability is 1 minus p. So value for 0 into 1 minus p. What about the other values? We don't need it because the probability is 0. Okay, so that will be equals to p. So this expected value of x will be equals to p for the Bernoulli random variable. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay.
Yes.
So this is how actually we find out the Bernoulli random variable probability or expected value. But they have also found it like that. Now an example is given, 2.26. Actually it is very easy. It is the PMF is given. What is the value of ER? ER will be 0 into probability of 0, that is 1 by 4, and then 2 into 3 by 4, that is equal to 3 by 2. So this example is the same as the expected value calculation of the Bernoulli random variable. Now we talk about expected value for geometric random variable. Now we need to find out what is the PMF of a geometric random variable. Okay, so let's see what is the PMF of a geometric random variable. Can you remember? Can
Yes,
anyone
sir.
can you help me?
Hmm.
What is that?
P 1 minus P to the power x minus 1.
1 in P into 1 minus P to the power x minus 1.
Minus 1.
This is the, and then of course 0 otherwise, isn't it? This is
Yes,
0
sir.
otherwise, and this value is for x equals to
1 to
1,
3, 4.
2, 3, up to infinity, isn't it?
Yes,
This
sir.
was the PMF for this expected, PMF for the geometric random variable. Now, to find out the expected value is what? X, px summation, isn't it? Now, what is this x? Look at that. This actually is the probability, isn't it? So we have this x, and the probability is p into 1 minus p to the power x minus 1. So this is our expected value of x, isn't it? And definitely this x value is from 1 to infinity, isn't it? So if it is the expected value, how to make it shorter, how to simplify it? Okay, now to simplify this one, we need to know some infinite series summation result. Okay, we actually know one result, which is p q to the power x, or not like that. It is something like x q to the power x. Okay, and if the summation is something like x equal to 1 to infinity, that value will be equals to q divided by 1 minus q whole square. That value we know. That value we know. Now we can use this value for this particular problem. How can we solve it? Let's see how can we solve it, and keep that in mind that this is we know. The thing is, remember one thing, p, this p value is a fixed value, probability of rejection. There is no x variable inside p. So can we take this p outside the summation? Can we?
Yes, sir. It is constant.
We can take it outside. So we can write it like p into summation of x equal to 1 to infinity, then x 1 minus p to the power x minus 1. So look at this one, 1 minus p. If I can take 1 minus p equals to q, let 1 minus p equals to q. 1 minus p is one constant, q is another constant. We can take this 1 minus p equal to q. So if it is like that, then actually what is this? We can write it like x into q to the power x minus 1, like this. Look at this, it is becoming almost similar kind of thing like this. Okay, so now what we can do, q to the power x minus 1 means what? Q to the power x minus 1 means q to the power x divided by q. Do you agree? Do you agree
Yes,
with
sir.
that?
Yes, sir.
So we can write this, that this q is another constant value. There is no variable inside the q. So we can take it outside,
Yes, sir.
and we can write p divided by q into summation of x equals to 1 to infinity x q to the power x. Now the thing is that part actually is the value we know, isn't it? So
Yes,
if
sir.
we know the value of that part, can we say that this is equals to P divided by Q into Q divided by 1 minus Q whole square? Can I say
Yes.
this one?
Yes, sir.
We can say that one. So, and we can cut this 2Q and we can write P divided by 1 minus Q whole square. Now, 1 minus P, look at this one. 1 minus P equal to Q. Can I say 1 minus Q equals to P?
Yes, sir.
So
Yes, sir.
we can put the value of 1 minus Q equals to P. So we can write it here, P divided by P square, or we can say
1 by P.
1 by P. So this expected value of X is actually equals to 1 by P. So we can say that for a geometric random variable, the expected value of X will be equals to 1 by P. Is it okay? And is it clear?
Yes, sir.
Is there any question? If not, then let's go to the next. Just see this. Look at this. The geometric random variable X has expected value Ex equal to 1 by P. And then they're taking the proof that they're making these things, and then ultimately they're finding 1 by P. Okay. So let's go to the next slide. Now we're talking about Poisson random variable, the problematic one, the Poisson random variable. So can we remember the PMF value for the Poisson random variable? Can we
Yes,
remember?
sir.
What is that?
A to the power x e to the power minus alpha by x
Factorial x.
factorial x. Yes,
Alpha
sir.
to the power x, e to the power minus alpha divided by factorial x. This is for x equals to 1, 2, 3, like this one infinity, and then 0 otherwise. Can we remember this one? The Poisson value is something like this one. Okay. Now again, we need to find out the expected value for this Poisson random variable. What is the expected value? We know that this one is equal to summation of x px, this one. So we can write summation definitely equal to x equal to 1 to infinity, and then this x will come, and then this px will come here. So that will be alpha to the power x e to the power minus alpha divided by factorial x. Okay. Now, how actually we will be proceed? We have to keep in mind one series that we have to keep in mind. What is that? Alpha to the power L e to the power minus alpha divided by factorial L, and summation L equals to 0 to infinity. If that is the case, then that will be equals to 1. That is our series that we know. Okay, there are many series we know actually. We have to know some logarithmic series, some exponential series, many series we know. And this is one of those series that we have to know. We have to keep in mind. Okay, so this is one series that we know already. Now we have, if we somehow we can bring our formula into this kind of thing, then we can put the value, and then we can simplify our expectation. Okay. Now the thing is, that is equal to what? We know that the factorial x equals to x into x minus 1 into x minus 2 into like this one up to 1. Can I say that this is equal to x into factorial x minus 1. Can I say that?
Yes, sir.
Sure.
So if it is like that, we can put it here, and then we can write it something like x alpha to the power x e to the power minus alpha divided by x into factorial x minus 1. And we can definitely easily cut it. And then we can write it something like this one. X equals to 1 infinity alpha to the power x e to the power minus alpha divided by factorial x minus 1. Now the thing is, look at this one. If I want to make this kind of thing, then whatever is in the lower side, like factorial L, alpha to the power, that particular thing should be there. So we have a factorial x minus 1, and in the upper side, we are having alpha to the power x. So again, we can actually make some things like alpha to the power x equals to alpha into alpha to the power x minus 1. We know that, isn't it? So if I write this one, can I say that this is equals to alpha into, because alpha is a constant value, constant thing, we can take it outside, and we can write alpha to the power x minus 1 e to the power minus alpha divided by factorial x minus 1. Can I do it?
Yes, sir. Alpha.
Yes, we can do it. We can do it. So alpha is a constant value, and if I take the alpha common, then there will be a minus 1 in the alpha to the power. Then that will be looking easier. Okay. Now the thing is, let x minus 1, let x minus 1 equals to L. Okay. Now I'm changing the variable from x to L. Now the thing is, we have to change their limit as well. When x equals to 1, then L equals to what?
0, sir.
0. When x equals to infinity, then L equals to what?
Infinity.
Infinity as well. So this limit, previously it was something like 1 to infinity. Now it will become L equals to 0 to infinity. And this becomes alpha to the power L e to the power minus alpha and then factorial L. Okay. So we now have actually found the way to put the value, because this is the same thing that we have told here. And this value is equal to what? This value is equal to what? 1,
Alpha or 1.
1, 1. I mean, this value is equal to 1 and the whole value is equal to alpha. Alpha. So this E of x now becomes the alpha. So we can say that this expected value of x for this Poisson random variable will be alpha. Is it clear? Is there any question?
No, sir.
Okay. So the thing is, we can now clear drawings and go to the next slide. Look at this answer. It is alpha, and we have the proof like this, and we can see the results, and this is the series that we know, and we put the value of the series equal to 1, and then we have found out the ex equals to alpha. Okay. Now we have solved 3 random variable families, and we have the other 3 random variable family result like this. And this will actually be the assignment number. This will actually be the assignment number 1. Assignment 1. Okay, the assignment 1, and the assignment 1 will be, the part 1 will be this one. This is the part 1. There is another part, I will come later on. The part 1 is to solve these 3 expected values for binomial, Pascal, and discrete uniform random variable. Okay, and the submission date is the next Sunday. That is 7 days you will get. You'll submit it by using the Google Classroom. I will give the assignment in the Google Classroom. So the first part is this one. Second part I will assign later on. Okay. The thing is, I'm clearing the drawings and I'm going to the next slide. Okay. So the thing is, the function of a random variable.
We need to prove those three, okay?
Yes, you need to prove those 3.
What you need to do.
Yes, you need to prove those 3, and also there are some other 6 variance values. You need to prove them as well. So this is the part 1 of the assignment, the 3 expected values of 3 random variables families. Okay, now actually I'm talking about a function of a random variable. What are the function of a random variable? The function of a random variable is the derived random variable. Look at this one. We will call. Can you see the screen?
Yes, sir.
Yes, sir.
Why is it telling that the screen sharing is paused?
Yes, sir.
They're telling the screen sharing is paused. Why it is like that?
We can see
Nothing
any-
is
Okay, good. So the thing is, remember one thing, function of a random variable. X is a random variable, we know. Now, if I'm telling that the Y is another random variable, which is a function of random variable, X, or we can say G of X. And that can be, say for example, X square plus 1. So X is a random variable and Y is a derived random variable if Y is a function of X. Okay, and function of X means some multiplication, addition, power like this. So if Y is equal to X square plus 1, then actually Y is a function of X. And Y, we can say that it is a derived random variable. What is the advantage of derived random variable? The advantage is, if we know the probability function of X, then we can directly find the expected value of Y from P of X. This is the advantage. We don't need to find out Py, but from the Px, we can find the expected value of Y. How? By using this formula. Look at this. Expected value of Y, that will be equals to mu Y, we know that. And that will be equals to summation of fx or gx pxx. Normally, what is the E of x? That is equal to x px summation, isn't it? But when I'm talking about EY, then instead of x, I will put function of x. Others are same. Do you understand? What is the gx? Gx is equal to x square plus 1. So we can write here summation of x square plus 1 and then px. Because this function is about x, so we can easily find out this summation because it is a function of x. So probability of x is enough to find the calculations, to find the summations. So this is called the derived random variable, or this is called a function of random variable. All right. So the function of random variable, we can find it easily. All right. Is there any question?
No, sir.
Okay. If not, then let's go for an example. Let's see the example. Okay. So this is example number 2.31, and here we are having a function of x. What is the function of x? Look at that. This is the y, which is equal to g of x, which is a function of x, and that this is the function of x. So the function of x or the y is given for two different ranges, and also the p of x is given, probability of x. Now they are telling you to find e of y. Okay, they're telling you to find out e of y. Now, how will we find that one? Okay,
We will use previous equation.
yes,
We will use previous equation for both of the cases. There is split. The function is split. I mean step function. So we will need to find for x is equal to 1 to 5, and then find 6 to 10, and then add them.
that is true. That is good. But the thing is, for the second function or second step, do we need to use it?
No, sir. It's a constant value.
It's a
So
constant value,
it will come outside the summation sign.
no problem.
We will actually p of x. We will actually,
What is the p of x for this 6 to 10?
It is stated that it is zero
Zero.
otherwise, so we should not.
Yes, yes.
So
This is zero
probability-
otherwise.
Yes.
So only actually probabilities are there for up to 4 value.
Yes, sir.
After then, there is the full region of the second one and some portion of the first one. Actually, we don't need to think about it
Yeah.
because they are zero. If I make this x into px, that px part is zero, so the whole part will be zero. So actually, this range, we don't need to think about it.
So upper limit of the summation will be 4 from 1
Right, right. So actually, what actually we will find, this ey will be equals to gx into px, and then a summation from x equal to what?
1 to 4. Go to 1.
1 to
Upper limit is
4.
4. sir.
Because we don't need to think about 5, 6, 7, 8, because for those 5, 6, 7, 8, these px values are 0.
Yes.
So that will actually be 0.
Yes.
So it is enough to add up to 4. All right. Now it is, I mean, this particular range value is 10.5 x minus 0.5 x square. And then this x equals to 1 to 4, and then pxx. Is it clear? Now just put the value of 1, 2, 3, 4, and this px is always constant. This is 1 by 4. All right. So we can easily find it out. There is 1 by 4 common, and then this we can say summation of x equals to 1 to 4, and then this 10.5x minus 0.5x square. Isn't it? Just put the value and
Yes.
find the result. Is it clear?
Yes.
So look at that. What is actually they are finding? They are finding the same thing. Okay, they are just putting the values and they are finding the result equal to 22.5 cents. All right. Is there any question?
No, sir.
Okay. Then we can go to the next slide. Okay, look at this one. Variance and standard deviation. Okay. The variance and standard deviation is what? This variance, when I'm talking about variance, this variance is actually, okay. sharing this stopped. Just a minute. Okay, the thing is, variance is what? Actually, the variance is something like this one. This is the variance. It is what? It is the expected value of x minus mu x. That is variation of the random variable from the mean, isn't it? We have a mean value mu x and we have a random variable x. So x minus mu x, this is the variation of random variable from the mean, and I'm taking the square value and then taking the average value. That is called the variance of x. And what is standard deviation? This is just the root of variance of x. Look at the theorem 2.13. Variance of ax actually is e of x square minus mu x square. Okay, e of x square minus mu of x, mu of x square. How to prove that one? For proving that one, we'll start from the definition of variance. And this definition of the variance is variance of x equals to e of x minus mu square, mu x square. Now, how can we start for this proof? Okay, look at this one. What is e of x? It is x px summation. If I say that the x minus mu x square, this is the x, then can I say that this is x minus mu x square into px summation? Can I say that? That because this is a g of x kind of thing, function of x kind of thing. Can I say it?
Yes, sir.
We can say it because it's a function of x. Now, if I just break it in different parts, something like a minus b square, that is x square plus mu x square minus 2 into x into mu x, that one into pxx. Can I do it? We
Yes,
can
sir.
do it. We can do it. And then can I say that this one is the same as x square into pxx? I'm just multiplying this one and then this one plus summation of mu x square into px plus again summation of, not plus, actually it is minus, it's a minus. Okay, then we can say that 2x x into pxx. Can I say it?
Yes, sir.
Okay, now let's cut this. be rewritten in this line. Look at that one. Can I say that equal, look at that, this particular part x square pxx, can I write it like expected value of x square, this one, because summation of x px equal to e of x, then summation of x square px should be e of x square. If I say that this is a function of x,
Yes, sir. You can see.
Yes, sir. Yes, sir.
okay, so we can say that. Now the thing is, look at this second portion, mu x square. What is mu x? Mu x is the mean value of the random variable x. Okay. Now the thing is, this mean value is a fixed value. Do you agree?
Sure.
Okay. So definitely this fixed value square also is a fixed value. So I can take this fixed value out of the summation sign. Can I do it? So can I say that this is equal to mu x square summation of pxx?
No,
Can I
sir,
do it?
so the boundary of x, is it fixed? I mean, the starting value of x and the ending value of x.
Of course. I mean, when you're talking about a sample, say for example, there is a s of x,
Okay.
isn't it?
Yes, sir.
So this x is fixed. Say for example, you are talking about rolling a dice. There are fixed number of outcomes: 1, 2, 3, 4, 5, 6. Is there any other outcome possible?
No, sir.
No.
Okay, sir. If the boundary is fixed, then mu x is also fixed.
Definitely, the boundary is fixed. You cannot have a you must have a universal set. You must have a
Sample.
sample space, isn't it?
Okay, sir.
So this mu x is a fixed value, and then we can take it like that one. Then we can say that this minus, we are having this 2 and mu x. These two are also fixed, isn't it? So 2 mu x can be taken outside, and then summation of x px. Now that thing can also be written like e of x square plus, now tell me, what about this one? X, I mean summation of pxx. What is this?
P of 1, I think.
Do you all agree?
I think it is P of 1 because if I.
This is 1. This is 1 because taking all the values of x, I mean all the probability value,
Okay, okay. Oh, so this is 1.
that will be equal to 1.
Then
So that will become mu x square. And then, actually this is not minus 2 mu x minus, this is into, isn't it? So minus 2 mu x, what is this one?
Mu x.
Mu x, this is the mu x, do you agree? X px summation, this is the mu x. So mu x into mu x, that comes mu x square. All right? And we have a plus mu x square, we have minus 2 mu x square. And that will be e of x square minus mu x square. Do you agree? Do you agree with this one? No, you don't agree.
Yes, sir.
So I think you are not agreeing with this one because there is no voice.
Yes, sir.
So this variance of x equals to this one, we have already proved it, isn't it? So this variance of x that we started with, that variance of x actually is equal to this e of x square minus mu x square. Okay, so this is the proof of this theorem. You know that the mu x and this e of x, they are same. That's why the same thing can be written like this way. Is there any question regarding this proof? Okay, there is no question. So let's go to the next slide.
sir, I forgot how mu x is equal to p of e of x. Can
Why
you
not? I mean, I have told you in the last class.
class? I just forgot. Sir. Mu x.
Yeah. Mu x and e of x is same. I told you. What is mu x? Mu x is summation divided by total number.
Okay.
What is e of x? E of x equal to x into px summation. I told you, I have given in an example, and I have told you that these two are same.
Okay, sir. Okay, sir. I got it.
Okay. So if you forgot, then see the last class
The last class.
slide. Then it will be you will understand. Proof is given. The proof is given like this one. Okay. Now we're talking about moments. Okay. Now I just told you that what is moment, and we were talking about e of x square. This is another kind of moment. When you're talking about e of x to the power n, then we are talking about nth moment. And when I'm talking about e of x square, what is that? This is the second moment, isn't it? When I'm talking about expected value of x, what is that?
The second moment.
This is second moment.
No,
This is the first
first
moment.
moment.
This is the first moment. So can I say that the variance equal to second moment minus first moment is square? Can I say that? If you can just follow the previous slide, the variance equal to second moment, this one minus first moment square. Just now we have proved.
Yes.
You have to keep something in your mind, in your memory. Just now I have told you, and just now you have forgot.
Oh, sorry.
Look at this one.
Yes, sir, I remember.
What is the
Yes, sir, I remember, sir.
what is the nth central moment? Nth central moment is expected value of x minus mu x whole to the power n. This is called nth central moment. So can I say that variance is a second central moment? Because variance is what?
Yes, sir.
Variance is expected value of x minus mu x whole square. So in the exam, if I tell you that prove that nth central moment,
So what is central moment?
central moment is actually you have heard this thing about moment. Moment is the Bhramuk. The force actually this moment is something like, say for example, the x, the random variable is how much deviated from the mean. That is the x minus mean, isn't it?
Yes, sir.
So when I'm talking about, say for example, a Gaussian distribution, the distribution is something like this. So the random variable x is not much deviated from the mean mu x. But if the distribution is something like that one, then I will say that the random variable x is far deviated from the mean mu x. So how the sample is distributed in the collection, that actually is, I mean, the Bhramuk, or I mean the variance. The variance is something like how flat or how steeper is the PDF, or probability distribution function in the or PMF. How distributed is the PMF? Okay. Central moment is something like that. This is also kind of thing. Central moment is also variance. Second central moment means what is the I mean uh, uh, say for example, random variable are distributed x minus mu x. Say for example, I'm talking about 1, 2, 2, 3, 3, 4, 4, 5. Okay. Now mean value is 3. Okay. Now the thing is, if I want to find out x minus mu x, then look at that. 1 minus 3 means what? Minus 2.
-2.
Then this one is -1, -1, 0, 0, 0, +1, +1, and 2. So if you just take a sum of x minus mu x, actually you will find a 0. That's why we use square, cube, or other nth central moment. We want to find out how this distribution is related with the mean, how flat or how steeper the distribution is from the mean. And to find that, a statistical element is used that is called the central moment, and this n terms actually is something which actually gives us some indication, because if the n equal to 1, actually you will not find any indication, because that value will always be 0.
So we need the magnitude, sir.
Yeah, we need some magnitude, or we need some power of that deviation, so that we can find a value which actually represents something about the distribution. So depending on n, what is the power of the central moment, that actually is defined. And variance is one kind of central moment, which is the second central moment, by which it is a measure of distribution of the samples inside the sample collection. Do you understand?
Yes, sir.
Okay, so this is the central moment. All right, and this nth moment is another kind of thing by which actually we find out the distribution of the samples. Now, why actually we are doing this? Just to find out this this variance. Now, another relation, another theorem is there. Variance of ax plus b equals to a square variance of x. Now, how do we prove it? Okay, how do we prove it? If I want to prove it, then we need to go from here. Let us take y equals to ax plus b. This ax plus b, I'm taking it as y. So definitely variance of y is the left hand side. Variance of y, isn't it? And we know what is variance of y. Variance of y is e to the expected value of y square minus mu y square. Do you agree?
Yes, sir.
Okay. Now there are two parts of this variance of y. One is expected value of y square. Another one is mu y square. So one by one, I want to find out what is expected value of y square and what is mu y square. Okay. So this expected value of y square equal to what? Let's put the value of y. Value of y is ax plus b. And if we put it here, then we can write it something like this: a square x square plus b square plus 2ax b. Okay, and that's it, isn't it? The thing is, we can write here e of a square x square plus expected value of b square plus expected value of 2axb. All right, look at that one. A is a constant value, so we can write a square expected value of x square, and then constant value, if I take the expected value, that will be same, so we can write b square directly. And also we can write this 2ab, okay, 2ab expected value of x, that is called mu x. Can I write it like this one?
Yes, sir.
Okay, so that, let's put it as equation 1. Now, what about this mu y square? Mu y square. What is mu y? Mu y is expected value of x or expected value of y square, isn't it? Expected value of y whole square. And what is the expected value of y? Expected value of ax plus b, which is whole square, which I can say that we can write it something like expected a into expected value of x means a mu x plus expected value of b is b whole square. Can I say that? Can I say that?
Yes, sir.
Okay.
Yes, sir.
Now, if you make a square, that is becoming a square mu x square plus b square plus 2ab mu x. Let's put it question number 2. Is it okay? Now in this left hand side, look at this. Left hand side, we are having this e of y square, mu y square, and we have found those two. Now if I put the values here, what is happening? A square, expected value of x square, or we don't need to write this one. We can write it like this, expected value of x square, then plus b square plus 2ab mu x minus a square mu x square minus b square minus 2ab mu x. So can I cut this one and this one? Can I do it?
Yes,
Can
sir.
I do it? Okay.
Yes.
Then there are two things left. I can take a square common and we can write it e of x square minus mu x square. And this is what?
Variance of x.
Variance of x, right? So we can write a square variance of x. So this actually is our right hand side, and we can say that the right hand side. Now, left hand side equal to right hand side. Proved. Is there any question?
No, sir.
All right. So there should not be any question regarding this proof. We can do it. All right. We can do it. So clear all drawings, and then let's go for the next slide. We have already proved it. Okay. Now in this theorem, we are having all these 6 variance values. 6 variance values. We need, this is the part 2 of our assignment. Assignment 1. We are having second part, and to prove these results. Okay. Previously we had 3 questions, and now we are having 6 questions. Total, there are 9 questions. So you have to submit this assignment within the next Sunday by using the Google Classroom. I will give the assignment in the Google Classroom maybe today, and then you will have the option to solve it and give the answer within the next Sunday. And remember one thing, in the next week, you will have an exam on chapter 1 by using Google form. Give it in your Google Classroom, and you will have this question in the Google Classroom, and then by using the Google Classroom, you will will answer the Google form quiz. I will announce the date in the next week. So just keep in mind
On chapter 1 only.
on chapter 1 only. On
Okay.
chapter 1
In
only.
the Google Classroom, you said MCQ questions only.
MCQ questions only. Okay, but that MCQ question needs some calculations. Okay, so so be careful about those calculations. There is a problem because there is no way to see the procedure. So if you make the mistake, then actually you will get 0. So actually I'm doing it because it is easy to check the script. Otherwise, if I want to check all the scripts by using the computer, it will be difficult. So just try to solve it. I mean, there will be 4 options, almost 4 options, maybe some cases more than 4 options. And then you have to choose the correct answer. So I hope that you will be able to understand, will be able to do in the first quiz. Okay. Any question is there regarding assignment and quiz? Okay. So thank you very much for attending the class. We are actually stopping the class today here. In the next class, we'll finish this chapter and we'll start the next chapter. All right. Any question? So if there is no question, we can stop sharing and we can just go for attendance. Okay, roll number 16 batch 49.
Present, sir.
16 batch 168. 16 batch 168. Absent. 17 batch 36. 17 batch 36. Absent. 162.
Yes, sir.
157.
Yes, sir.
177.
Yes, sir.
181.
Present, sir.
183. 183. Absent. 159.
Yes, sir.
101. 18 batch.
Present, sir.
102.
Yes, sir.
103. 103. Fardeen Sohel 103. Absent. 104.
Yes, sir.
105.
Present, sir.
106.
Yes, sir.
107.
Present, sir.
108.
Yes, sir.
110.
Yes, sir.
12.
Yes, sir.
13.
Yes, sir.
14.
Yes, sir.
15.
Present, sir.
16.
Yes, sir.
17.
Yes, sir.
18. Roll number 18. Roll
Yes,
number
sir. 18, sir. 18.
18. 19.
Assalamualaikum, sir. Yes, sir.
19.
Present, sir.
20.
Present, sir.
21.
Yes, sir.
22.
Yes, sir.
23.
Yes, sir.
24.
Present, sir.
25.
Present, sir.
26.
Yes, sir.
27.
Present.
28.
Yes, sir.
29. 29. Muhammad Makam ul Hasan 129. Absent.
Sir,
130.
I'm 103, sir.
পরে আসো।
Okay, sir.
130.
Present, sir.
131.
Yes, sir.
132. 132. 132. Raya. Absent. 133.
Yes, sir.
134.
Yes, sir.
136. 136. Absent. 137.
Yes, sir.
138.
Present, sir.
139.
Present, sir.
140.
Present, sir.
141.
Present, sir.
142. 142. Ibrahim. Absent in many classes. Tell him to come in the class. He? Ke present?
Present, sir. 132 present.
132 na, are baba, 142. 132 present, তুমি এখন আসছো কেন? তুমি পরে আসবা, পরে বলবা। If any of you come late, then tell me at the end of the class attendance, not in the middle of the attendance. Okay. 142 absent. 145.
Yes, sir.
146.
Present, sir.
147.
Yes, sir.
148.
Yes, sir.
Okay, is there anyone absent or is there anyone haven't mentioned in the attendance?
18 batch 136 sir.
132 present, sir. Yes, sir. 132 present.
হ্যাঁ 132 present, ঠিক আছে। আর কে?
136 sir.
136.
Sir, 103.
103. হ্যাঁ, তারপরে আর is there anyone else? কে? কেউ কি অ্যাটেন্ডেন্স দিচ্ছে? Is there anyone? Is there anyone absent or want to give your attendance? No, I think. So thank you very much.